Alright guys, this is your 5.2 notes and examples, discrete probability distributions. Recall from earlier sections, discrete means we have gaps between possible values in our data. Or you can think of it as, usually, not always, but usually it's data that results from a count when we deal with discrete. But we have, the big thing is we have gaps between the data. Right? Probability, obviously, likelihood, a measure of likelihood. And distribution, that means how the data is spread apart over the possible likely values. So when you put all these together, we're looking at all the different possible discrete values of a particular variable and the probability it takes on those possible values. So here's an example. Alright, a particular baseball player had 209 hits a season. This is the probability distribution of the number of hits the player obtained in a single game. Okay, so he can get no hits all the way up to 5 hits in a game. So we're being asked to compute and interpret the mean of this. So the formula for the mean is the sum of the x's, the measurements, the 0, 1, 2, 3, 4, 5, times the probability of those measurements. So what this means is 0 times 0.1748 plus 1 times, I should put that in parentheses instead of a dot, times 0.4342, right, plus dot dot dot, plus all the way to 5 times 0.0371. Okay, I'm going to do that on my calculator real quick. Alright, so here is the probability distribution multiplied x times the probability of x all the way through for every value. If you notice in there, I've got this is not playing any role in it. You could always leave the 0 times the value out if you want, and then the 1 times the value, you could just put the probability in there, but then everything beyond that you would want to put it in there. Alright, now do that, I get 1.5073. So 1.5073. Alright, compute and interpret the mean. Don't forget to do this part, and interpret the mean of the random variable x. So this means, on average we would expect 1.5 roughly hits per game. So on average 1.5073 hits per game, and then again this is assuming that he goes to bat 5 times in a game. So that's what we would interpret that as. Okay, it is a mean, so it's an average. Alright, and compute the standard deviation. The standard deviation, there's a couple different formulas for it, but the standard deviation, is the square root of the sum of the measurements minus the mean squared, right, just like it used to be, but now we're multiplying times the probability of x. So to save us all those steps, it's going to be several steps to do to get that standard deviation. I'm going to show you how to do it on your calculator. If you press the stat menu, go into the editor, so stat enter, and then put in your distribution. Right, and notice I have the values that x can take on in list 1. I have the probabilities in list 2. Right, once I do that, I press the stat button, and I go over and I want to get the one variable stats. Now people confuse it because there's 2 rows, they want to use 2 variable stats. Okay, but the only thing that's varying, the only random variable we have is x. So there's just one variable. This is a probability row. It doesn't have anything to do with being a second variable. So this one variable stats, but we do need to tell it that there's 2 lists. There's list 1 where the x's are, comma, list 2 where the probabilities are. And then when we do that, we see there's our mean, 1.5073, and here's our standard deviation, 1.217. Now if we would have done all this steps, we would have come out with this. but I wanted you to see that that's what we get for the mean and standard deviation. Okay, now that we have a mean and standard deviation, we can do things like take that 1.5073 and add 2 of these standard deviations to it. 2 times 1.217, and that's like a rare value. Anything above 3.94 hits in a game is rare. So it's rare when he gets 4 and 5 hits. And notice the numbers are both below 5% as well. So probability wise, they're both considered rare. So we're not asked to do that here, but I'm just reminding you that with a mean and standard deviation, you can compute rare values. So it's just like it was before. And also remember that rare events are the ones that have below 5% probability of happening. Alright, determine something is a discrete probability distribution. So for it to be discrete, there has to be gaps between values. So that part's satisfied. For the probability part, these probabilities have to add to 1, and there can't be anything above 1 or below 0. So if I add up these probabilities, right, there's the values of just the probabilities, not this times that like it was before. But if I'm just determining if it's a probability, then they have to add to 1. They do. There's none above 1, there's none below 0, so this does work. So yes, this is a valid probability distribution. Okay, but for instance, if this had been a negative, or if any of these, like if that had been like 1.28 or 1.21, then that would be no. Okay, so it has to be no negative values and nothing below or nothing above 1. Alright, another one where we need to find the mean and standard deviation. So there's a 0.04 probability the best of 7 series will last 4 games. That probability will last 5, that will last 6, and that will last 7. Verify this is a probability distribution. So once again, we're just adding those numbers and showing that they add to 1. Okay, we already see that there's nothing negative or above 1, so that part's satisfied, but we need to add the 4 numbers. Alright, so adding the 4 numbers up, I get 1, so that means it is going to be a valid probability distribution. Alright, now, to find the mean and standard deviation, again, I'm going to use the table. I've already got data in there from the last problem. Remember, we can hit highlight, hit clear, and enter for both of these lists. Clear, enter, and now I can start over. Okay, so a 7-game series has to go 4 games if it's best of 7. So it has to go at least 4, 5, 6, or possibly 7. Those are the 4 possible values. Okay, and then the probabilities that it goes 4 games is 0.1584, 5 is 0.2891, 6 is oops, I missed one. Oh, I missed the first one. 0.0084, 0.1584, 0.2891, and 0.5441. Alright, so there is the possible values of the number of games. There's the probabilities. Now I hit stat, calc, 1var stats, and then I tell it L1, comma, L2. Alright, there's my mean, 6.37 to 2 decimal places. So again, it's that calculator always returns the same notation. It's always going to give you X bar, but the mean notation for this is that mu, that population mean, with a little subscript of X. So that was 6.37. And then the standard deviation is equal to 0.775 roughly. Alright, so the expectation is this will go on average 6.37 games that'll be played in this series, and then that's the standard deviation. Now, is it unusual for a team to sweep winning in 4 games? Yes. I mean, there's the probability of a sweep, 4 games. Way less than 0.05. Okay, but also you could use 6.37 minus 2 standard deviations is considered rare, 0.775, and you get 4.82. Anything less than this would be considered rare. So 4 would be considered rare again in both cases. Alright, and then when we got this probability distribution, this is the number of jurors that serve on a jury, and this is the number, X represents the number that are Mexican American that are on the jury. Alright, so find the probability of exactly 6 Mexican Americans. Well, this is a probability distribution, so the probability of 6 is the one that's right there with 6. So point 0.016. Okay, find the probability of 6 or fewer. Now we're taking 6 and going all the way down to 0. So according to this, it's 0 plus 0 plus 0 plus 0. Alright, for all of these, and then I don't start really until these 3. So I'm going to add 0.06 or 0.16 plus 0.003 plus 0.001, and then the rest are a whole bunch of zeros, so they're not adding anything to it. So 0.02 chance total. Alright, and then this says which probability is relevant for determining whether 6 jurors among 12 is unusually low. So if you're asked to determine if something is unusually low, you need to start at that particular number and go all the way down to the smallest value that's possible. Alright, so in this situation it's B, because you want to go all the way down from that number to 0. And then for unusually high, you would do that number up to the highest number. Okay, you add all those probabilities. So when you see that, when you see in a discrete probability distribution, if something is unusually low or unusually high, you need to do not just that number, but that number all the way down or that number all the way up, depending on the scenario. Insurance company is going to charge this 21-year-old male premium of $500 for a year of $50,000 coverage. So because a 21-year-old male has a virtual certainty of probability of living, they want to know what, from the perspective of the 21-year-old male, what are the two values of the different outcomes? Well, he can lose $500 if he lives, or he can gain the $50,000 minus the $500, because if he no matter what, if he lives or dies, he's going to have to pay that $500 premium. So that would be $49,500 if he dies. Alright, now what's the expected value for a 21-year-old male who buys the insurance? Well, if you think about it, again, we can go to our calculator to put, just so you can see it. These are the two possible values. He can lose $500 as a 0.999 or 99.9% chance of that happening, or he can gain $49,500. There's a 0.000 or 0.001 or 0.1% chance of that happening. And then if we use our calculator to do the one of our stats, L1, L2, this would, I mean, there's only two things. This would be easy to just multiply it out by hand. But anyway, we get expected value of negative $450. Alright, and then this one says, what would be the cost of the insurance company breaks even? What would they be charging for it, for them to break even instead of making a profit? Well, that happens when the probability X is our cost. We don't know that. So this is the if he's going to live, this is the amount he's going to lose. If that's equal to the probability that he dies, so $50,000 minus X is what he gains if he dies. This is the probability he dies. Probability he lives. What happens if he lives? This is the amount lost. So that happens if these two things are equal. Alright, so that's just 0.99x. I'm going to set that equal to, if I distribute this, 0.001 distributed through would make that just 50. And then obviously this is going to be a minus 0.001x. Alright, and then I add this over here to this. If I add that over, I get 0.001x added to 0.99x, that's 1x, equals 50. So they would need to charge $50 to break even.